Good afternoon, ladies and gentlemen. Thank you for visiting this last webinar in the session we have in the large thermal heat storage. This is the fourth session, and we welcome you again, and I will explain some details. My name is Bas Potsdok. I'm of IF Technology and the business developer in high temperature ATOS systems and the international business. And for today, I'm your host. This webinar is supported by the RVO and TKI Urban Energy. And it is a program which has its origin from the IEA, Energy Storage Task 39. And in the first webinar, I have explained in more detail about this Task 39. So you can have a look back on that. The guidelines for this webinar, we have disabled all your cameras and mics. So the way how you can communicate is dropping your questions in a Q&A box. And then during the sessions, we try to answer them. And at the end of the session, all the questions and answers will become available. It's not possible to raise your digital hands, but that's the way how you can use it is using a Q&A box. All the webinars are recorded, and including the presentations and fact sheets, they will all become available afterwards. So please enjoy also this last session. And the last session deals about the tank thermal energy storage system. In the previous session, we went into the aquifer and borehole and pitch thermal energy storage system, all technologies which are very relevant in balancing the heat supply and the heat demand, as you can see in the valve tube figure, which is on the left. So our presenters for today will explain why it is important and which role tank storage can play. Here you can find the details of task 39. We have a couple of key objectives and we have subtask. And you can have a look also on the website to read more about this task 39. These are all the partners which are working on this task. And for today, the agenda is that first we will invite Geoffrey to explain about what is TTES. He will explain about a case in Berlin. And the second session will be done by Ruud van der Bos of Groene Warmte, Dutch company. And in that way, we will deal with this topic. So for now, I will give the floor to Geoffrey. Geoffrey is a French engineer specialized in modeling, analysis, and design of renewable thermal energy systems, including means of heat production, like solar, waste heat, biomass heat pumps, and thermal storage. He's working in Denmark at Plan Energy since 2019, and Geoffrey has been involved in several international collaboration research projects involving modeling of seasonal thermal energy storages, and has performed techno-economical feasibility studies for various countries worldwide. He will talking today about tank thermal energy storage, introducing the technology as well as its common use in Denmark and abroad. Geoffrey, the floor is yours.
Thank you for the introduction, Bas. And I will share my screen. There we go. So thank you again for the introduction and for the opportunity to speak at this webinar, the last of the series. My name is Geoffrey. I'm an energy systems engineer, and within IEA ES Task 39, I'm actually a subtask leader in subtask D, which is responsible for dissemination. And I'm part of the Danish consortium of Task 39, which receives support from our National Energy Agency funding program, EUDP. I will make a lot of references to the work by IEA Task 39, and that's because we're really trying to democratize large thermal energy storages. So as Bas said, my presentation will introduce what tank thermal energy storage is and show some use cases and examples. But first, what does it look like and what is it used for? Well, tank thermal energy storages is one of the four main large thermal energy storages, which are actually defined in our task as sensible thermal energy storages, no phase change material involved. They are designed to store at least 1 gigawatt hour of heat per year and at atmospheric pressure, so no pressurized systems are included. And the stored heat should be suitable for discharge into district heating networks. This presentation will focus on above ground thermal energy, tank thermal energy storages, which is the most common kind, and Ruud will then present underground tank thermal energy storages afterwards, but I will focus on above ground as mentioned. So what is a TTES? It's basically a giant thermos, and it's built in five main steps. The first step is building the foundation of the tank to make sure that it sits perfectly on the ground. Then you build the roof of the tank, and then you build from the top down, so top to the bottom, one level at a time. You build one level, and then you lift it up, and then you build the next level. The third step, and it's actually running in parallel to the second step, is to build diffusers inside the tank to be able to let water flow in and out of the tank. And then finally, you install insulation around and on top of the tank in order to make sure that there are limited heat losses. And the last step actually is to put cladding around the tank such that the insulation material is protected, but it's also an opportunity to decorate the tank and integrate it into its environment. So these are the five main steps for building a TTES. In Denmark, and I will start by giving the Danish point of view, TTES are basically everywhere and are usually coupled to biomass boilers, waste incinerators, CHP plants, and they enable a flexible use of those heat production units. And they are connected to big district heating networks. That's not the only place where we find TTES in Denmark. They also find in solar district heating systems, which are a Danish specialty. In Denmark, there are 1.6 million square meter of solar district heating collectors installed. So it's solar thermal collectors connected to district heating. And it's usually very large installations. And as you can see on this graph, Denmark is at the top here on the left. And an installation like this is characterized by solar thermal field that you can see here in the bottom. These are examples of a project in Denmark, and almost always with a daily thermal storage to make sure that the production corresponds to the consumption of heat. So why large thermal energy storages for district heating? I've been mentioning district heating a lot already. But why is it that we have those large thermal energy storages? Well, first of all, it's because heat is inexpensive to store at large scale. How inexpensive? We're speaking of 10 euro per kilowatt hour, less than 1 euro per kilowatt hour at large scale. Here you see the graph, and it shows you how the specific cost of thermal energy storage evolve when increasing the size. This is for an individual house on the left, 160 liters. And if you go to district heating size, several thousands of cubic meters, then you fall down by a huge factor. And this is why it is interesting to go for those large thermal energy storages, is because they're the bigger, the better, and the cheaper. And in comparison, pumped hydro storage is much more expensive. It never goes under 100 euro per kilowatt hour of storage capacity. Another point about large thermal energy storages is that they enable the use of renewable. They provide flexibility in district heating systems. I've already shown some examples in Denmark. They increase the share of renewables in the system and the use of waste heat. They can help with peak shaving. And larger storages are needed to serve district heating systems, but other large-scale applications such as industrial, and they help further reduce specific costs of renewables and primary energy use. And in that sense, there is another task called task 35, which is also from the energy storage IEA task. And in this task, we have shown that using thermal energy storage or double the amount of thermal energy storage will help save a lot of primary energy consumption. So in these ages where we're really trying to reduce our consumption of energy, of primary energy, it's a very good tool to have. And then last question of general question about large thermal energy storage in general. Why is it less known? Well, often it's coupled to district heating or big infrastructure, so it's usually far from the city centers. It's a local solution, unlike electricity storage, so there is not many international debates about this topic. There are less use cases. One storage is enough to cover a huge demand, which is why we see them less, and it's less high tech. And some would even say that it's less sexy, but I would disagree with that fact. I think this tank thermal energy storage here in Germany is quite sexy. Now going to the advantages of specifically tank thermal energy storages. Well, first of all, it's a very simple solution, and it has many advantages. It can run at high temperatures, close to 100 degrees if you have absolutely no pressure, just above 100 degrees if you use damp at the top of the tank, and 115 degrees if you use two-zoned storages, which is a specific kind of non-pressurized tank thermal energy storage. These technologies are very low maintenance. They have a long lifetime. We're talking about 30 years at least. They have very high charge and discharge capacities of heat. Several hundred of megawatts is already possible with this technology. It's very well known. It can be found basically everywhere. And there are little to no restrictions with regards to the underground conditions to implement these tank thermal energy storages. Of course, you need a ground that is sufficiently solid, but this can be fixed if it's not the case by building foundations with reinforcements in the soil. Now, the disadvantages of this very simple solution is that it has a higher specific price than the other LTES that have been shown in the previous webinars. And they also have a visual impact when they are above ground, and which is, you can see here an example on the right. It's a tank thermal energy storage in Heidelberg in Germany. It's a two-zoned water storage, but you can see they have made an architectural facing, and there's also a restaurant at the top. So there are many options to bypass these visual impacts. Now, going to some details and some use cases for tank thermal energy storages. We have a first example with solar district heating, as I was mentioning earlier, that there's a lot of them in Denmark. And there's also this example of district heating in Berlin. Going to the first case, in Orlum, this is a typical solar district heating installation in Denmark. It has a solar collector area of 16,000 square meter, a tank thermal energy storage of 3,600 cubic meter, and you can see it here in the back. And then 21% of the heat demand of the local district heating network is covered by this solar heat. In that case, the auxiliary heat sources are a gas CHP, a gas boiler, and an electric boiler. And of course, all of these means of heat production can use the tank thermal energy storage in the winter, for example, in order to have a better flexible use. If you have cheap electricity price, there's a lot of wind, for example, in Denmark in the winter sometimes, then you can store cheap electricity in the form of heat and then reuse it later to do some peak shaving, for instance. So that's the first example that I have today. The second example is that of Berlin, and it's the biggest tank thermal energy storage that has ever been built. It's 56,000 cubic meters. Normally, the upper limit is around 50,000 cubic meters or even 40,000 cubic meters. So this one is very big. It has a charge and discharge capacity of 200 megawatts, a thermal output and input, and it's designed to make 70 to 120 cycles of charge discharge per year. The main purpose of this T-test is to increase fossil-free heat share on the district heating network in Berlin while ensuring flexibility and security of supply. It is also used to manage and to withhold the pressure in the district heated network of Berlin. So it is equipped with a huge bank of pumps. As you can see here, this is an extract from the brochure that we have made for Task 39. This tank is going to be also used as power to heat means of storage. So again, when electricity prices will be low, a heat pump that will go up to, well, it's not only a heat pump, but there will be a heat pump, will be able to store up to 120 megawatts of thermal output. I think that's more or less what there was to say about this example. Yes. If you are interested in learning more about large thermal energy storages, please feel free to contact Task 39. There is also Task 41, which is more focused on economics of energy storage. Feel free to ask the task manager of those tasks or your IEA-ES TCP delegate, or you can send me a message and I can add you to our distribution list, which is a mailing list. Now, this states Danish international activities within ELTES. It's actually very specific to IEA-ES Task 39. So everyone in this task has been contributing to this goal. We will distribute at the end of this task, which is ending this year, information materials for all 4 stages of ELTES projects. And those 4 stages of projects are starting with the opportunity phase, where you determine whether an ELTES is a good it's a good addition to your system, energy system or not. And there are several actors that are involved here. Policymakers have quite an important role. Local residents can be involved as well. District heating network operators and project developers. The next phase is the design phase, in which all the technical design is determined for implementing the ELTES. Then there's the tender phase, in which everything is prepared to offer tender and to get many offers, competitive offers for the ELTES, and then finish implementation and operations. And the idea is that Task 39 will provide information materials for all stages of ELTES projects, and tank thermal energy storage projects are also following these 4 stages. And just to give you a brochure preview, here you can see the brochure, which is the first deliverable that we have finished in this task. And there is a part that is introducing large thermal energy storage more in detail, giving more advantages and presenting the 4 technologies. And then there's a second part about use cases, which is more focused on giving concrete technical examples, but that also present the different technologies and what are their technical limits. So if you're interested, again, please send a mail, reach out to IEA ES TCP delegates or me, and we'll be in touch. Thank you for listening. I went a bit fast, but then we have probably a bit more time to answer some questions.
Thank you very much, Geoffrey. A very nice presentation, which gives a very good overview of the. Just looking for my own presentation. Oh, I think that's the wrong one. This one. Yep. Will be very good. There are probably some questions. I saw some questions appearing up in the Q&A box. So for the people who are new or just entering after the introduction, please don't raise your hand, but please drop your questions in the Q&A box, and then we will try to answer them directly, or we have them right now. David, do you have some questions which we can ask Geoffrey?
Yeah. There were definitely some questions. Thank you very much for your presentation, first of all, Geoffrey. Very interesting information and nice cases as well. And especially regarding the cases, there were a few questions that really popped up after you were telling about Berlin. People were definitely curious about, the biggest tank storage and what it's for, what it's used for, and things like that. So the first one is a question that also kind of popped up. You mentioned it was a daily storage, I believe. So that does that mean that it's drained every day, or that it's and then warmed up every day again, or how does that work? What is the function in the system there?
So it is definitely a daily/weekly storage. It is meant to balance the district heating network on a daily basis. So it will be charged and discharged, as I said, 70 to 120 times a year. So it means pretty much every second or third day. And it will not be fully charged or fully discharged. It will be partially charged and partially discharged all the time, basically. And the full cycle is when you have charged fully up to the capacity. But it will usually not do it in one go. It will do it in several steps, and it will try to optimize the production and the consumption all the time.
Yeah.
So that's how it's meant to work.
And especially when it's coupled with the heat pump in the future, then that's even more so, of course. Thanks.
Yes.
Do you also have an idea of the price for the Berlin installation as
yes, well? I saw that question. I'm just checking if I have the value. I think the only public information about this project is the total investment cost, which is, if I'm not mistaken, it has been made public, 50 million euros.
Yep.
But if you look at the specific price that corresponds to, it's way higher than the price of what a tank thermal energy storage is supposed to cost. Okay. So it's about 1,000 euro per cubic meter. It's a bit less, and that is simply because it's not only for the tank thermal energy storage, but it's the tank plus everything around it, the connection pipes, the heat exchangers, the pumps that are helping ensuring the pressure on the network. So it's all of that included, and it's a pretty big charge and discharge capacity. So it's actually a good question, and it's complicated to answer to that question because there are many things in every LTES project. There is both the storage itself and the equipment around it, and you cannot get one without the other.
Yeah.
So usually it makes more sense to have a global price like this, 50 million. But then it makes it more complicated to compare the different cases. So it's always let's say a tricky question to answer, but that is the answer for that case. And if you want to know other cases, then you should reach out to other experts or to other project owners to get some inputs. But Plan Energy is definitely one of the actors that have some references in that sense.
Yeah. So the specific price is higher than the TITAS usually, but because of those extra installations. I was also wondering, does pressurizing the system make the system more expensive as well, or a lot more expensive?
Yes, definitely. Having a pressurized tank will multiply the investment cost by 5, basically, or potentially even more. So it makes it much more complicated, and that's because the mechanical constraints in the tank are much higher. I can see that there was a question, 15 or 50 million. It's 50 million. So this has been answered.
Yeah, 50, correct, right? Yeah.
David and Geoffrey, may I also ask you, you are the sub-task leader for the dissemination of this S39, so you have a good overview of the different technologies which were dealt in this work group. In the previous webinar, there was a question, okay, can you give kind of overview, or can you maybe give suggestion when should you choose which technology, because we have ATAS, we have pit storage, we have thermal tank storage, so when do you choose which technology? Can you give that in a very brief?
Very complicated question, Bas.
Yes, I know.
No pressure.
But basically the underground context will play a huge role on what is possible at all. In general, I would say you should always consider all possibilities. But if there is no aquifer in your area, then you will rule out aquifer from the start. If the ground is filled with water that is flowing, then you will rule out any kind of underground thermal energy storage like BTES or PTES, because that will just absorb all the heat that is being taken. You basically need to find a compromise between the space available, between the amount of energy that you need to store, and between the soil local soil conditions and properties. And that means that there is no general answer on how to choose the technology, but these are the 3 factors that you need to look at to know which technologies you have to look into.
Thank you, Geoffrey. I think that's really useful because that are, I think, good considerations you have to make before, when you want to judge which technology. So.
And in the brochure, there is also a graph summarizing what the different technologies can achieve in terms of heating power, heating output, and input. So this is also quite useful to be able to choose. If you want something that can release a lot of power, then it will be very complicated to do with borehole thermal energy storage. But if you want to go in large scale storage, then the tank has limited capacities, because the above ground tank at least is limited to 50,000 cubic meters, and that's it. A borehole can go much higher, for example.
May I thank you very much, Geoffrey, for your clear presentation and also for generating this useful discussion. Then
thank you.
I will move on to the next speaker, Ruud van den Bos. Ruud is a Dutch project developer with a background in the built environment, developing renewable district heating and cooling systems for residential areas and business parks. Within this project, he applies different kinds of storage, such as aquifers and TITAS. And within this project, he is responsible for design, business case, financing, and governance. He has also worked on the development of the EcoVat storage system and therefore knows a lot about this technology and the possibilities. He will be talking today about underground thermal energy storage. Ruud, the floor is yours.
Thanks a lot, Bas. Thanks for having me here today. I just finished answering lots of very good questions in the chat, so Jeffrey can take over that task right now. Perfect. I'm going to share my screen.
Yep, it works.
Yes, it works. Right. Yes, thanks a lot. So my name is Ruud van den Bos, and I work at Groene Warmte. And as you can see in the right top, I have prepared some a small agenda of the slides, an overview. So we're talking about underground storage, tank storage in this part. Jeffrey already mentioned above ground storages. And there are some developments in the Netherlands and in Europe to look at underground storage, underground tanks. And this is has a lot of similarities, but also some differences compared to above ground. So using the same overview within the four main large thermal energy storage systems, we have the tank, and now we'll focus on the underground tanks. So looking at, so I'm following up on Jeffrey's presentation about the general advantages of tanks, so I won't go into that here. But going underground has some advantages and disadvantages compared to above ground. And the main reason usually is to have a smaller visual impact after construction. This is when the large volumes need to be integrated within a district heating system, and the location is within the city or urban environment, and high volumes of storage above ground are not very suitable. And the other thing is that it's also possible to make very large volumes underground. So above ground storage volumes are somehow limited. The Berlin case was very big, but there is a limit to that. And once you want to go bigger, you probably want to have it underground. And then it also starts to look a bit more like, for example, the pit storage technologies that have been presented in the other webinar. When storing underground and large volumes, it usually also becomes possible to store for longer periods, and you'll have less losses due to the soil temperature. It's usually warmer in winter than outside temperature, but also there is less convection losses due to winds blowing against the above ground tank compared to the underground tank. And obviously, you could make double use of space. So there are designs already to look at maybe to use the top for extra functions. For example, in Germany, there has been made a green park on top of a tank. On the other hand, there are some disadvantages. The costs can be higher, and this is highly depending on the scale of the project and also the location, so the soil conditions. So there's a feasibility in the end, technical both and economical, is depending on those conditions. Meaning groundwater can influence the cost of construction, but it can also be that it's due to the groundwater situation that it's not legally possible to build there. And rocky soil is also usually challenging. It will result in a higher construction cost. The construction time of underground tanks is usually longer, and it has a higher impact during construction, as you'll have lots of earth or rock to dispose of while digging the hole for the tank. You'll need to remove these volumes, and if this is in city center area, you need to take this into account. The underground storage tanks are unpressurized, so above ground they can be pressurized, as Geoffrey already mentioned. However, the underground storage tanks are all unpressurized, which means they can store temperatures that are below 100 degrees. This presentation will show two main example initiatives. That will be the EcoVAD and the GigaTES project. So the EcoVAD project is a construction principle based on prefabricated elements. And the GigaTES is based on having insulation inside a bore pile wall. And I know there are also variations on this concept, and those are all being studied and looked into. However, this is also one of the possibilities. And the EcoVAD principle has a diaphragm wall for the construction, and the insulation is attached to the inside of it. Well, there's lots of different terms most people probably never heard about before, so I will briefly explain them in the next slides to elaborate on how that works. So the GigaTES project, it's a project in at the moment being studied further in near the area of Vienna. And the project first had been going on from 2018 till 22, and now is having a follow-up, which is called the Scale-Up project. So the name GigaTES refers to the first period, and below in the links, which we'll share in the slides later, anyone can look it up and see what the latest status of those projects is. The volume in the GigaTES project for the tank that was looked into was 100,000 cubic meters. That's a very large volume. And the roof was a floating roof. And this is comparable to the pit storage floating roofs that have been discussed in the other webinars. And then there was an option for insulation. And this was done using bore pile walls, hollow bore pile walls, which will be filled with foam glass gravel. Foam glass is basically a glass, so a natural material, not harmful for the environment, and it has some unique characteristics, namely that it does not absorb water, just like a normal insulation for your house, which means that it will keep its insulating properties over time, even while getting moist or wet. And it is also able to withstand higher temperatures like these and high pressures. There are currently several different options being evaluated for several parts of this construction principle, such as the materials of liners that need to protect the tank from the inside. And this is a challenging thing because underground storage tanks you can't really easily access to later, or only with a high cost, compared to tanks above ground that are better accessible, and this creates high quality standards and demands for all materials being used in the ground. The goal of the project is to have a demonstration built in 2 years. And in the right bottom, you can see a visualization of the scale-up projects. Yeah. Then the EcoVault project. I'm a little bit biased because I know a little bit more about this technology, but therefore I will also be able to explain a little bit more about it. And if there are more questions on the GigaTest project, I think Geoffrey might be able to answer them as well. So the EcoVault has been in development since 2013, and a small demonstration has been built in 2017. And right now, the optional volumes are between 10,000 and 100,000 cubic meters. The design has a supporting roof, so not a floating roof, which means it has a central column in the middle supporting the roof with which has beams and concrete slabs on the top. And the installation is attached to precast modules. And the precast modules are basically consistent of concrete attached with foam glass insulation. I have a few more slides going into the construction principle. So the construction also has 5 steps, coincidentally, just like the above ground. It doesn't start with foundation. In the end, that is not necessary, since the net pressure of the tank downward is the same as the previous soil, basically. So the main challenge is to make sure the tank does not collapse from the pressure of the outward soil. And this is the function of the diaphragm wall, which is a construction cylinder. And I have a slide on that in the next slide on the diaphragm wall. And then when the diaphragm wall is built, then the tank is excavated. The tank can be full with water at that point or still dry. This depends a bit on the local situation. Then a concrete bottom is cast. Then the precast modules are installed, and then the roof is made. So a diaphragm wall, or a D-wall, is a very common technology in construction, and it's used for underground parking garages and subway stations. So that's in many countries, there's experience with this. And usually these designs are obviously made to last a very long time. So have at least a life expectancy of 100 years, obviously for preserving those stations. The walls are watertight and suitable for deep constructions, such as TTS. If you want to know more about how these things exactly work and go about, there's a lot of information and videos about that on the internet if you want to dig a little deeper. The precast modules is a homemade innovation of EcoVault, and the main purpose of this is to fix insulation inside the tank and have it there for forever, basically. And also here, foam glass insulation is used, which is shown by the black part here. So here we see modules which have like roughly 30 centimeters of insulation. And this insulation, these modules are made in a controlled factory with a very high precision, which will then make sure that during construction they can be put together very securely without any deviations. The concrete attached to the insulation is there for structural stability of the module, but it's not for the structural integrity of the tank. So the previously mentioned diaphragm wall is there to have the tank safe and structurally sound. And the concrete here also functions as a downward force of the insulation to prevent the insulation from floating in case there is a high groundwater level in the tank, so that the elements will be underwater. Also on the website of EcoVatt, there's 2 videos, one of 3 minutes of the whole construction and one of 10 minutes of the fabrication of these modules. And then you can see each step, how it's made. And this is very interesting to see if you want to know more. So first demonstration has been built, was a relatively small volume, but the proof of technology and construction was thereby proven. So the bigger sizes work on the same principle with precast modules. However, there were some improvements made after the first tank. So better roof design, better module design, and better diffuser design. And the diffuser, for those who don't know, as Jeffrey already mentioned, the diffuser is the inlet nozzle connected to the piping, which will have the inflow of the cold or hot water into the tank to store it or to discharge it. There are several projects being looked into, one of which I can't tell the location or name here, but there has been a feasibility study already more than a year ago, and we're looking into the next steps. And the volume of the tank is 60,000 cubic meters and about 100 megawatts of power output. And this makes it roughly a weekly storage tank for large district heating application. And there were some questions in the chat before about what is the storage duration of tanks. Usually this is a daily storage, such as with the solar heating or to provide the morning or afternoon heat demand peak in the district heating. And while at this moment we see more and more integration of renewable power on the grid, such as wind, and this has led that some district heating systems are looking into weekly storage to also include the wind profiles of renewable low-cost power, and combined with power to heat and storage to include this in the systems. So that's the application here. And on this picture, you can see the required space for this project for construction. So the tank of 43 meters in diameter has a wall and then a perimeter around it, but only on one side a large construction site is needed. And that's because of the crane of the tank to excavate it and to place the modules is a rolling crane, which is rolling over the edge on the profile of the tank, which makes it able to stand in there. So it doesn't need to be constructed next to the tank, which reduces space requirement, but it also doesn't pressurize on the side of the tank. So it's an ideal way to install the crane during construction. Something about the integration of underground tanks. The underground tank is an unpressurized tank, and usually district heating systems have a much higher pressure system. This introduces the need for a heat exchanger between the tank and the system, as you can see here, the part D. And it also requires like a pump facility with a pump named P. And this also makes sure that the heat quality and pressure in the district heating system can be maintained. As with underground storage tanks, the water quality cannot be maintained on the level of above ground storage tanks. the pump station required needs to be near the tank, and it needs to be also partially submerged, that the pump is basically below the water level, top of the water level of the tank. When looking at application and integration, most of the tanks that are designed are used for daily, weekly storage in large district heating systems. But the future goal also for the GigaTest project and the Scale-up project, but also for the EcoVault project, is to go towards seasonal storage. However, at this point, usually the costs are too high to make a feasible business case out of it. While for weekly storage, there seems to be a business case in most large district heating systems. And I think personally, the way forward is to improve the technology and have experience in weekly storage applications, and then see from there how the technology can evolve. When you have other alternatives for seasonal storage, such as ATES or PTES, those are probably the preferable technologies for seasonal at this point.
1 minute left, Ruud.
Well, perfect. Thanks. Something about legal part. You always need to take into account when looking at a location that there is no contaminated soil. Otherwise, there will be extra permitting and extra costs included to clean the soil that you'll excavate. There have to be done studies on the groundwater effect, on the temperatures that it creates, and the possible microbiological reactions. But that's also the case with other underground storages. Most importantly, structural integrity. So the construction principles should always be safe. And then think about permitting, logistics, disposal of soils, rocks, etc. So yeah, that was it. If you scan the QR, then you can reach my LinkedIn, or just send me an email if you want to know more.
Okay, thank you very much, Ruud. Very interesting and also very visual, so that really helps us to get a good impression of on the technology. And I see in the chat many also very practical questions, so I think it will be good to go to that.
Yep.
Yes.
Thanks for the questions, Ruud. One of the first questions that popped up was also about isolation, whether or not there's isolation at the bottom of the tank, is what some people were curious about.
There's two options. Speaking for the EcoVault principle, I know that there are two options, whether to include it or not. For the GigaTest project, I don't know. It is, let's say, when there's a low groundwater level and you can have a dry tank, then it's easier to install insulation on the bottom than when the tank has a higher groundwater level and that it's always full with water.
Yeah. All right. Yeah, good. Thanks for that as well. One thing that I was curious about, and obviously it depends on the size of the system and how many are being developed, but could you say something about the prices for these installations?
That's going to be hard, and it's very dependent on size and soil conditions. So, for example, the rocky soil bottoms make a very different cost than soft soil. But if anyone has like a it's not a sales target here, but if anyone has a location and a desired size of the tank, then we can really easily provide a budget within the day about what we think roughly it will cost. Cool. If there's any cases, just let me know, and we'll do this free of charge.
Clear. There were also a few questions more regarding, also just in general, the water. So where does the water in the tank come from is a very practical question. But I, for example, also saw that during the installation, there appeared to be water in the hole already. So I was curious about that situation.
So the scale-up project or the GigaTest project, I know they're considering to have a dry pit during construction and then just fill it with water. I'm assuming just water from the just normal tap water. Yeah, tap water, drinking water, or there will be a treatment plant if they use maybe something from a river or something. I've also seen these ideas. If they have a small treatment plant to use the water from a local natural water source. If it's not possible, when it's possible to make a dry pit, usually go for that option because it's cheaper and it just has less risk. But if there's a high groundwater level, this is not possible, not always possible, because the upward pressure is just way too high to make a structure that can keep the tank down. So then you'll have, during excavation, you'll have a tank that will automatically fill with groundwater from the bottom. And you can allow this if the groundwater doesn't have any negative substances, but you can also prevent the tank from filling with groundwater by having a higher groundwater level in the tank than the higher level in the tank than the groundwater around the tank. And this, if you then have clean water in the tank, it will always keep by pressure, it will keep the groundwater from entering the tank. And so then you will have to excavate the tank while always having it full with water. So then you'll have underwater excavation, basically.
Yep. Clear. No, thanks for all those different. This was something that was also brought up in the pit storage webinar. So it's nice to see those comparisons, and sometimes people ask the difference as well. So that's a good one.
Maybe the last quick question, David.
Yeah, that sounds good. Maybe can you also say something about the temperature losses in this system? And I'm guessing it's higher than probably above ground because of the insulation effects of the ground.
Yeah, so it loses less than above ground. Way less, and also so that has a few reasons, because it's the temperature in the soil is higher, but also less wind effects, and depending on the size, but also if you have larger volumes, then you usually have less losses. Looking on a seasonal basis, you can see that the losses will, like for example, from a 15,000 cubic meter volume, the losses will probably about 25%, maybe 30%. If you go to higher volumes, the losses will be roughly 10%, a bit comparable to pit storage systems on a seasonal basis. When you use the tanks for short-term storage, like weekly or daily, then you'll also use it more. You charge and discharge it more, and then if you look at the actual loss per charge cycle, that will be then really low, since if you have like 30% on a year or on a half a year, then the daily losses are relatively low. And there could be more losses due to other things during charging and discharging, also with the heat exchanger and the temperature degradation with the heat exchanger, and that also is basically loss.
Okay,
good point.
Thank you guys very much for your very clear presentation and answering the questions, also hosting the questions, David. Due to the time, we have to finish, and I just want to announce 2 upcoming events. So in maybe to start with the last one, in March 28, we will arrange a high temperature ATIS symposium. So you can have a look at the iftechnology.nl website to register. And the other event is in Offenburg in Germany, which is on the 28th of February. And then it will deal about the technologies which has been dealt also in this webinar series. So you can go to the link and register also for this event. Now, and with this, we come to an end of this 4 session. I would like to thank all the speakers and especially David also for hosting this and helping us with, to let everything run very smoothly. So thank you very much for that. And I also would like to thank all the people who has registered and which were present during the presentations. It was very nice to see how many people participated in this series. And I thank you very much for participating and have a good day. Thank you. Bye-bye.
Thank you very much, everybody. Bye.
Thanks a lot.
Mm-hmm.